Take the number 6 and write down every number that divides it apart from 6 itself. 1, 2, and 3. Now add those up. 1 plus 2 plus 3 is 6. The number is exactly equal to the sum of its own divisors. That almost never happens, and the next number it happens to is 28. The parts of 28 are 1, 2, 4, 7, and 14, and those 5 numbers add up to 28 on the nose. After that, the gaps get enormous. The third one is 496, the fourth is 8,128, the fifth is already past 33 million. Numbers that equal the sum of their own divisors are called perfect numbers, and they are scattered incredibly thinly across the number line. Here is the thing nobody has ever explained. After more than 2,000 years of looking, every single perfect number anyone has ever found is even. 6 is even, 28 is even, all 5 of those are even, and so are all of the ones discovered since, every last one. So the question almost asks itself, is there an odd perfect number somewhere out there? Nobody knows. Not whether it is large, not where it might be, whether one exists at all. This is, by most accounts, the oldest unsolved problem in all of mathematics, and by the end of this you will understand exactly why it is so stubborn. To feel why perfect numbers are so rare, it helps to have one clean way of testing any number at all. For a number, add up all of its divisors, this time including the number itself. Call that total its divisor sum. For 6, the divisors are 1, 2, 3, and 6, and they add to 12, which is exactly twice 6. That is the real definition of perfect, stated cleanly. A number is perfect when its divisor sum comes out to exactly twice the number. Twice, no more, and no less. And that word exactly is doing enormous work, because almost no number manages it. Take 12. Its parts, 1, 2, 3, 4, and 6, add up to 16, which overshoots 12. Numbers that overshoot like that are called abundant. Now take 10. Its parts, 1, 2, and 5, add up to only 8, which fall short. Numbers that fall short are called deficient, and the deficient ones are everywhere. Out of the first 100 numbers, 75 are deficient, 22 are abundant, and exactly 2, 6, and 28 sit perfectly balanced between the two camps. Perfect numbers are the knife edge, the precise boundary where the divisor sum lands neither over nor under, but dead on twice the number. Most numbers miss that edge by a mile, so where do the even perfect numbers come from? Euclid worked that out, more than 2,000 years ago, and his recipe is beautiful. It runs on a special kind of prime. Start with a power of 2 and subtract 1. 2 squared is 4, minus 1 is 3, and 3 is prime. 2 cubed is 8, minus 1 is 7, prime again. Keep going and you get 31, then 127, primes both. A prime of that shape, one less than a power of 2, is called a Mersenne prime. They are the raw material. Euclid's recipe takes one of these and pairs it with the power of 2 just beneath it. Take the Mersenne prime 3 and multiply it by 2, and you get 6, the first perfect number. Take 7, multiply it by 4, and you get 28. Take 31, multiply by 16, and you land on 496. Take 127, multiply by 64, and out comes 8,128. Every time you feed in a Mersenne prime, this recipe hands you back a perfect number, and you can prove it always works. It is a clean, guaranteed machine for manufacturing even perfect numbers, one for each Mersenne prime. For 2,000 years that left a natural worry. Euclid's recipe makes perfect numbers, but does it make all of them? Could there be an even perfect number hiding somewhere that his machine never produces? Leonhard Euler settled it around the 1740s. He proved the exact reverse of Euclid's direction. Every even perfect number, without exception, has to come from that recipe. If a number is even and perfect, then it must be a power of 2 multiplied by the matching Mersenne prime, full stop. There is no other shape it can take. So Euclid's machine does not merely make some even perfect numbers, it makes all of them, and the two results lock together into one complete description. That is about as good as an answer in mathematics ever gets. The even perfect numbers are completely understood. We know precisely where each one comes from. We can list them in order, and finding the next one is just a matter of finding the next Mersenne prime, which is its own famous search. The even side of this problem is, for all practical purposes, closed. Notice the one word that has been quietly carrying every result so far: even. Euclid's recipe builds even numbers because it always has a factor of 2 in it. Euler's theorem only speaks about numbers that are even to begin with. The entire beautiful theory has nothing whatsoever to say about odd numbers, and that is the crack the whole mystery lives in. So here is the question, sharpened to a point. We have a perfect machine for even perfect numbers, and a proof that it catches every one of them. Is there a perfect number that is odd? The honest answer is that nobody knows, and people have been not knowing for a very long time. The question goes back to the ancient Greeks, to Nicomachus around the 1st century, who listed the first 4 perfect numbers and wondered aloud about their patterns, getting some of his guesses wrong. It has been worked on by essentially every major figure in number theory since, and it is still open today. Not almost solved. Not solved except for some edge cases, genuinely, completely open. We do not know whether a single odd perfect number exists anywhere in the infinite stretch of whole numbers. What makes it so maddening is that the odd case feels like it should be answerable by the same tools, and it just is not. The recipe needs a factor of 2, so it cannot reach an odd number. Euler's proof leans on the number being even at a key step, so it falls silent the moment you drop that assumption. Every clean handle we have on perfect numbers was built for the even world. Walk across the line into the odd world, and you are suddenly standing in the dark, with 2,500 years of mathematics behind you and almost nothing in your hands. If you cannot prove an odd perfect number is impossible, the obvious move is to go looking for one. So people did by hand at first, and then with everything computers could throw at it. You can run the test yourself on a computer in a few seconds. Take every odd number, one after another, add up its divisors, and check whether the total comes out to exactly twice the number. Do it for every odd number up to 10 million, and you find exactly nothing. The same search, run over the even numbers, immediately turns up 6, 28, 496, and 8,128, right where they should be. The machine works. It catches the even ones on cue. On the odd side, it just keeps coming back empty, mile after mile. And the real searches go almost unimaginably further than 10 million. It has now been checked, by careful computation, that there is no odd perfect number below 10 to the 1500. That is a 1 followed by 1500 zeros, a number so large that writing it out would fill pages. Every odd number underneath that colossal bound has effectively been ruled out. But here is the honest part, and it matters. None of that is a proof. Checking numbers one at a time, even out to 10 to the 1500, only tells you there is no small odd perfect number. It says nothing about what might be waiting further out. An empty search is evidence. It is not the same thing as knowing. The number line does not run out, so you can never finish looking. Now, mathematicians have not been searching blindly. Alongside the search, they have been slowly building a description of what an odd perfect number would have to look like if it exists. Think of it as a wanted poster, assembled one proven feature at a time. Start with Euler again. He showed that any odd perfect number has to have a very particular skeleton. It must be one special prime, raised to a power, multiplied by a perfect square, and both that prime and its power have to leave a remainder of 1 when divided by 4. A direct consequence is that an odd perfect number, if it exists, is itself one more than a multiple of 4. That alone is a strong constraint, proven beyond doubt, and every result that followed has been hung on this frame. And the rest of the poster is a list of demands, each one a theorem with a name attached. It has been proven that an odd perfect number must be built from at least 9 different prime numbers. Counting repeats, it must have at least 101 prime factors in total. Its largest prime factor has to be bigger than 100 million. Its second largest has to exceed 10,000, and even its third largest has to be over 100. And of course, the whole number has to be larger than 10 to the 1500. Pile all of that together and you are describing a monster, an odd number larger than almost anything in physics, stitched together from at least 100 carefully arranged prime factors, balanced so precisely that its divisors sum to exactly twice itself. So the obvious feeling, looking at that poster, is that surely no such number can exist. The conditions are so heavy, so specific, so absurdly demanding, that they must eventually crush each other and leave no room at all. That feeling is exactly the trap. Here is the strange truth at the center of this problem. Every one of those conditions is real and proven, and yet not one of them, and no combination of them found so far, actually contradicts the others. They squeeze the possible odd perfect number into a smaller and smaller corner of the number line. They make it rarer and stranger and harder to picture, but they have never quite closed the door. There is always still room left. A number that satisfied all of these demands at once has never been shown to be impossible. It has only ever been shown to be enormous. And that is the whole difficulty in one sentence. Proving something does not exist is a completely different kind of task from failing to find it. To settle this for good, you would have to show that the demands on the poster are genuinely incompatible, that they cannot all be met by any number whatsoever. Nobody has managed that. The constraints keep getting tighter every few years. The lower bound keeps climbing. The list of required prime factors keeps growing. And still the gap between extremely unlikely and provably impossible has not been crossed. Most mathematicians who work on it suspect, quietly, that no odd perfect number exists. But suspecting is not proving, and on this question the difference is everything. So that is the shape of the oldest open question in mathematics. A perfect number equals the sum of its own divisors, 6 and 28, and the rare giants after them. The even ones are completely understood, pinned down by Euclid and Euler to a single clean recipe, and the odd ones sit in a hole that all of that machinery simply cannot reach. We can describe the odd perfect number in extraordinary detail. We know it would be larger than 10 to the 1500, that it would carry at least 101 prime factors, that it would wear Euler's exact skeleton. We have searched past bounds so large they barely fit on a page. And after all of that, we still cannot say the one thing that would end it. Whether the thing we have described so carefully is real, or whether it is a perfectly consistent ghost that happens never to occur. If there is one thing to carry away from all of this, it is that in mathematics, knowing a great deal about something is not the same as knowing whether it exists. We have a portrait of the odd perfect number, detailed enough to recognize one on sight, and not one shred of proof that it can ever be drawn. 2,500 years in, the question Euclid's contemporaries could already ask is still waiting for an answer. Maybe it will be you who finally settles it. This was part of a series on the questions that have outlasted everyone who tried them. Stay for the rest.